Good morning and welcome everyone to our webinar for today, which is having a look at generative topology optimization and how it can revolutionize your design process. So our agenda for today, first we're going to be having a look at what's available in our simulation suite so that we can get an idea for where Creo's generative design tools fit into the design process. We'll then be having a deeper dive into what is generative topology optimization, which is the main focus for today's webinar, and then what is the generative design extension, which is a sort of an add-on that we will be looking at in the future. And then we'll have a look at the typical workflow that you would follow when using generative topology optimization, and then why should you use this tool. Then we'll be diving into a demonstration with Lefunofuno. And lastly, we'll compare the results that we get from his demonstration to what the original model had that we had a look at. And then we'll be looking at the Q&A. Okay, so this is the general design process. We start off with your concepts, you then work on a final design, take it to prototyping, and finally manufacturing. So typically what we've had a look at is, with our simulation tools, is high fidelity tools or traditional analysis tools. So things like your Creo Simulate or Creo Answer simulation that are typically used at the end of the design process because they're usually seen as too time consuming in the early to mid stages of the design process. This can sometimes lead to making compromises in the design when late stage changes are required. For example, adding ribs to increase strength at the cost of extra mass. Since simulation is only done at later stages, and if any errors are found, there will be a lot of rework, thus increasing the design cycle time. So what PDC is looking to do is improve how we design in the concept phase. They want to break down the wall between the two worlds of modeling and simulation. So the way they're doing that is by introducing capabilities such as autonomous design through generative design and instantaneous simulation through Creo Simulation Live. So we have the Creo Simulation Live tool, which sits at the concept and goes up to the mid sort of stages of your final design process, whereas Creo Simulation is looking at the later stages of your design process. And then we have the tool that we're looking at today, which is our generative topology optimization, which fits into our generative design modules. And that also works in the concept phase, but also goes into a bit into the mid sort of phase of your design stage. And if you did miss out on our Creo Simulation Live webinar, you can find it in our webinars playlist on our YouTube channel. So product development teams really need a simulation tool that is used right at the start of the process to ensure that concepts that are produced meet the design criteria right from the start. If you're not meeting those goals right from the start, you might have to do, well, as we usually do, we come up with many different concepts before selecting one to proceed with. So what PDC did is they acquired a company called Frustrum. They are an advanced generative design software company. So now their technology has been deeply integrated directly into Creo. And incorporating this into your design process can just really radically change how you design and how quickly you can do it now. And because this sits at the early phase of the development process, it complements our other simulation offerings such as Creo Simulate, which would be used to validate your design with that high fidelity simulation when you need it. So what exactly is generative topology optimization, or GTO, as we call it for short? So GTO is a means of autonomously creating optimal designs from a set of system design requirements With GTO, it's easy to set up a design study, defining the objectives, constraints, materials, and even the manufacturing processes that you want to use. And it quickly yields a parametric manufacturable design that can be further refined. So this could be an example of what you end up with after using generative topology optimization. But how do we get there? So our inputs. What we first need to define is some starting geometry. The starting geometry is the space that the computer will be allowed to create the actual design in. So you specify what that is. Then you go and specify the preserved geometry. Preserved geometry is geometry that has to be there. So it might be part or a section of the component that interfaces with another component or has some or other load or constraint applied to it. And then we have excluded geometry. So if this part has to fit into an assembly, where maybe there's another part that has to slide in there, or maybe we need a gap for some other reason, maybe there's some airflow or something that has to come through there, we can specify that geometry in there in red as being excluded, so nothing's allowed to be created in that area. Then we go and specify loads and constraints and preferred materials, just as you would with any other simulation that you might be used to. Then we go ahead and look at the criteria. So this is where it sort of differs to what you might be used to with other simulation tools. So you can specify constraints such as it must be symmetrical around a certain plane. And you can even go and specify the manufacturing process limitations that you want to take into account. And of course, we need a goal. So the goal in most of these cases is to reduce mass. Reducing mass is typically a pretty good metric to work with, because reducing mass can really improve the performance of a lot of different areas in engineering. Okay, and then what is generative design? So generative design is an add-on extension that is sort of complementary to GTO, Generative Topology Optimization. So whereas GTO runs locally on the user's machine to optimize geometry, solving for the active design criteria and material, multiple design criteria can be defined, but each is solved separately. GDX is a cloud-based add-on which provides high-performance computing and advanced tools to compare, interrogate, and select the optimal design. So GTO is really just the start of what you need to be able to do full-on generative design. You can see in the image on screen, what you typically do is define your criteria in GTO, like what we'll be doing today, and then you send it off to the cloud to get back a whole bunch of results. So we won't be getting into this detail today, but it might be a topic for the future that we'll have a look at. Okay, so what is the typical generative topology optimization workflow? So the typical workflow is very similar to what you'd already be used to. But firstly, would be creating the geometry with the GTO tool. But because your geometry then is based on criteria and constraints right from the start, subsequent phases of the process are sped up too. So after you've gone and created the geometry using GTO, you would then go and recreate the design. So in this case, what we're doing, or how we can do it, is we can automatically create this design using the built-in tools, and we'll show you how this works in the demonstration. And the importance of doing this step compared to this step is that this geometry is actual BREP geometry. So it means it can be manufactured. So you can program your milling machines or whatever it is your 3D printers based on this geometry, whereas this geometry here is actually just tessellated sort of facets, which wouldn't be usable. Typically, this phase would be done manually with other topology optimization tools out there, but in this case, it's done directly within Creo and done automatically for you. So once you're done with the recreation, you might need to go ahead and do some refinement. So you're not always going to end up with a perfect set of geometries from the results here. There might be a few minor changes that you need to make, maybe adding in some extra rounds and things that you've removed. You can bring those back in, whatever, refine exactly what you need to and validate it. And that's where you do that validation with Creo Simulate or Creo Answer Simulation. And lastly, you would take it through to manufacturing using the chosen method that you chose right at the start of the process. That could be machining, casting, or even 3D printing. So again, all of these are accounted for right at the start. So it really speeds up the entire process. And the great thing about all of this is that all of these steps happen inside Creo. So your models are all linked and up to date, and there's no exporting and importing required. So what are we actually striving to achieve here? So typically engineers want to deliver designs that are right the first time. I mean, who doesn't want to do something right the first time? So if you can produce the best design as soon as possible, that's a win-win for everyone. And then secondly, they want to deliver an optimal design that meets the criteria and objectives. And typically in engineering, we don't want to over-engineer or over-design something. We want it to meet the criteria perfectly. Of course, with our safety factors included. And companies typically want to deliver designs that are optimized for cost reduction and for profitability. It all comes down to the numbers at the end of the day. And delivering high quality designs that reduce the aftermarket cost and increase customer satisfaction. And of course, they want a competitive advantage. So if they can deliver breakthrough innovation that delivers on that competitive advantage, they should be able to charge a price premium. So at the end of the day, it does come down to the numbers. So the solution must deliver value to the business that makes it worthwhile investing in technology like this. How can this help? So firstly, it can help you speed up your time to market and new product introduction, bringing products to market faster than ever before. You can increase your product innovation and competitive differentiation, optimize designs to improve product quality and performance, which I think is critical, and eliminate over-engineered products and late-stage errors, so reducing your rework and scrap. So it's actually used this technology already as Volvo Trucks. So one of their key objectives with all their new vehicles going forward is really reducing their emissions. And one of the ways that they can do that is by reducing mass of the overall product, because then there's less work for the engines to do, whether that's, I guess, if that's an internal combustion engine, a hybrid, or a fully electric vehicle. So what they did here was they took a look at one of the components that's in the engine bay, and they actually sent this design out to Penn State University and asked them to redesign it. And they did. They came back with a solution like this, which is a big improvement compared to what they originally had. But lastly, what they did was they actually ran through the same inputs or the same criteria that they needed, but using the generative topology optimization, and they came back with a solution like this, which I mean is quite radically different to what we see they started with. And I mean, the weight reduction is huge. It's 75% weight reduction. But on top of that, they even reduced the peak stress reduction. So sort of a win-win in both scenarios here, which is, I think that's pretty awesome. Of course, our manufacturing techniques might have to change, but it might be worth it if we could do this and really get the benefits out of it. Today's demonstration will be done by Lufunofuno Chidada, one of our application engineers. He's currently completing his honors in mechanical engineering at the University of Pretoria. In the scenario that we've given him, he works for a mountain bike manufacturing company. They are continuously improving their products by optimizing their designs to be as light as possible, but still strong enough to deal with the high stresses the bikes are under. He is in the R&D department and investigating alternative suspension designs that could be lighter, but still strong enough to do what they need to. At the moment, the company has been sticking with the same old design and just optimizing it where possible, but only achieving marginal gains. So his goals and objectives for the session are to reduce the mass of the component, or what the original component is, while retaining its strength. And he needs to design these new concepts before lunchtime. He's been given the stress guideline by the company's analyst, which is around 60 megapascals maximum von Mises stress. And he's going to be working on this lower link, which is where the bottom part of the suspension joins onto the frame, and it also attaches onto the rear shock. And that's it highlighted there. Okay, over to you, Lufunofuno.
Hi, Ross. Thank you for that. As Ross mentioned, I am Lufunofuno Chidada, and I will be taking you through this section of the demo. All right. So, as Ross had mentioned, I'll be working on this link. So this is the original part. I've been told to sort of to come up with a new design for it. Currently, let's have a quick look at that mass there that we have. It seems we're sitting at around about 182 kilograms there. So I'm going to just try and see if I can simplify this thing here. All right, so now with generative technology optimization, the application is within Creo parametrics, so you don't have to open any other file or any other software. You don't need to export or move any data that you have. All you need is the data. All you need is just your data, the design that you want, and then you're able to do that quickly. All right, so we're going to start here. So so something with this link is that it's got interfaces around it. That's the links from the bikes, the spring as well. So now with that in mind, then we know that there are interfaces that we need to make sure that we have, I'll use the word preserved in this case. So when it comes to generative topology optimization, you need to tell the software that this is what I want to keep because I need to connect to something, and then this is the material that you can play around with because this is the design space that I want you to work on, or maybe, and this is the area that I don't want you to do anything about. So we're going to look at our design space for this specific model. So I've decided that my starting geometry will be more or less similar to what the original model is, but I just created more mass so that I have a little bit more to play with. So this will be my starting geometry. I'm just going to hide that again. And then my preserved body, which is what I want to keep. These are my interfaces from the link, if you saw that bike picture there. So this is what this is all that I need for this model, and then I'm just going to say, hey, keep this for me, and then do what you need to do to get me a final design. In some situations, you might have cavities or bars that are going through your part. You might have to add what is called extruded geometry as well. And this tells the software, do this area here or this volume here, do not do anything at all. Like in any engineering design, the constraints determine, or your input determines what your output is. So in this case, our input would be our constraints. In this case, I've chosen to fix the one side of the link and then add forces as per my my scenario there, so that so that I can get the design that is able to meet its application. So in whatever design that you have, your load cases will decide what kind of a simulation or what kind of result you come up with. I have decided to go for a fixed constraint this side just to prevent rigid body movement, and then my loads are the two there. Sorry about that. And the next, so after you have your design space set up and you have your load set up, the next thing that you want to do is your design criteria. So your design criteria is basically the sort of guidelines for what you want your Creo to work on. For this case, I'm going to say I just need you to keep 25% of that volume that I had there for my design space, and I'm going to choose the symmetry constraint for a start. So this is me basically saying, hey, I need this thing to be the same on either side. This could be either for aesthetic reasons, or maybe you just want it to be symmetric, depending on the design that you need. So from then on, I can go and set up my study settings. I have the option of either going for speed or going for detail. So if it's speed, it might not be as accurate, but if it's the bar is on the higher side on the detail side, it means that it will be a bit slower, but you get more detail on that one. So for the sake of this demonstration and the sake of time, I'm going to go for speed this time here. All right, so we have our design space set up. We have our what we want to preserve. We have our models. We have our fixed constraints as well. We have our design criteria. What comes next is to optimize that design. So optimizing the design is basically allowing the software itself to come up with the design for you. As engineers, we usually prefer corners, right angles. We want things that we can measure, you know. So now with your generative topology optimization, this now removes that biases now, and also now introduces us to design that we would have never thought of if we had to go if we had to do it ourselves, you know. And this also saves us time. It also saves us it also gives us a little bit more room to play with when it comes to creativity, as well as the changes that we need to make, because then now we are all we need to worry about is the boundary conditions of our system, and then we let Creo itself come up with that design. As you can see on the screen there, it's already generating the form that it has selected per se, with according to the design criteria that I have given it, and so far I must say it actually looks very nice. So imagine if you had time to sit and you had to do this manually. It will take you a lot of time, changing iterations, moving up and going from maybe exchanging information with someone else in order for you to make sure that this one meets this criteria. But here you are with a software that is able to do all of that for you, and all you need to do is just input the surrounding constraint. All right, there we go. It's done, and this is what I have. Just going to have a quick simulation of that. So the input that I had received was that the original model was around 60 MPa, and I had to make sure that I go underneath that. Clearly, from the model that I have here, I have surpassed that by far, and I'm happy with that. So from then on now, I'm able to generate that design. This is basically where Creo goes into creating that geometry using freestyle. Obviously, if I had to do this, it would take a whole lot of time, but now I have the freedom, or rather the option to allow the software to do it for me. And that is what generative topology optimization is about. We're not only optimizing the parts and the models, but we're also optimizing how you work, your workflow, the time it takes for you to do certain analysis to improve or change certain designs. And this now allows you to get your product out there into the market a whole lot faster, which also gives you that competitive edge. So yes, so now that means that now you have more time you have more time to be more innovative, you have more time to do a bit more, and also maybe also improve or increase your product range, and all of that with being able to keep to be able to keep your reputation in terms of your products and your models living up to the name, and that is your brand name. All right, so something else that I should highlight here is that now with this one here, reconstructing that geometry, that the model that it can pop up, since we use we went for speed as opposed to high detail, you also have now the option to send it out, or rather move it on to the next person for them to do a much more detailed analysis on your model, so that you are able to validate those designs and make sure that when you are releasing the designs, you are confident with what it is that you are putting out there in the market. And so for this case here, I had selected the four, rather the preserved bodies as what I wanted to keep. Sometimes you maybe want to keep a whole lot more, you have the option of what you call this thing of multi-body design, which allows you to create multiple bodies in one part. And this is where you are able to now say these volumes within that, instead of doing assemblies, but rather you have that single part within the same environment. You're able to create more complex geometry for your more extensive for your more advanced designs, because as you can see, this one is a simple design, just so that we can demonstrate that that ability that comes with generative topology optimization. Okay, I see that it was taking long for a reason. Something does seem to have not gone right. All right, so now you can see from there what it is that did not go well. Okay. All right, cool. All right, so now generative topology optimization, that you have the option to see exactly what it is that has gone wrong. As you can see from the error on the side, that it was just an error in the reconstruction section of it, of this one here, which is not a big issue, but for the sake of time, I'm not going to go into solving this one right away, but I do have another model that is ready to go, and I'm just going to continue from that. To call it okay. All right, so this is what it would have turned out to be had it managed to reconstruct that geometry, as we can see there. All right, so now, as we saw with that quick simulation, I have met the criteria for the maximum stress. I just want to quickly check if I have met the criteria for the mass. So we started at 180. Okay, if I work that out, that gives me about 93 grams. So that's essentially just over half, or just below half of that, which means that I have also met that criteria as well. And look at that, in such a short space of time, I was able to generate I was able to create a design that can be able to be used for the new product. All right, let's say, for example, now I wanted to change this concept. Let's say now I want to go and say, hey, let's do something that we can 3D print. I have the option to add that constraints. We have different constraints such as the build direction, the parting line, and the linear extrude. Now, the build direction is for when you want to do your 3D printing. Your parting line is when you want to do your molding. Your linear extrude is when you want to do more of your traditional machining. Okay, so in this case, I'm going to add that build direction. I want it to build. I'm going to use that top one there. I'm also going to add the material spread. So basically the material spread is me saying how it should accommodate the load parts. The higher it is, then I have more load parts, and the lower it is, it has got less. So let me just use the value 80 there. I still want to keep that 25 there, and then we're going to run that again. So now imagine how you would work traditionally. Generating one will take you quite a lot of time. Now imagine if you need to do another one. So now this is essentially that key point with generative topology optimization, that you can do more in less time, and not only just more, but better designs as well. So we're just gonna let it run now. And then when it's done there, we are able to see what it has come up with for us on that one there.
So what we're looking at on the screen here is the original design that Lefuno had to start with, set up with the same constraints and loads and everything as what he's just done. And then the first concept that he came up with, which was using very, very minimal constraints. So sort of just letting the computer do what it needed. So it was set up this is obviously from a previous run, set up with similar constraints, but also the same constraints, but only similar run settings. It might have been on some higher detail. Can't actually which one that was from. But the main things that we did here was retaining an acceptable von Mises stress. It was even better, I think. And it was lower than the yield stress of the material, which is, of course, lowered the cost of the materials, or, well, in other words, we actually used less raw materials in the design. So if we are using additive manufacturing, we're definitely using less material. It looks like this part could have been machined originally. So I guess it does depend on which manufacturing process you decide to use. But we are using less raw material at the end of the day. And then the performance of the suspension would also be improved because there's now less weight for the suspension to control. And yes, although the overall bike is only very slightly lighter, I think we say 90 grams, this is only one part being improved, a very tiny part. So doing this over multiple parts could add up to make a noticeable difference. And I think lastly, we did this in minutes compared to days. Yes, okay, there's a simulation still running, but it's still probably only going to take a couple more minutes to run, and we've come up with a few concepts already. Whereas if you were to go from scratch, you would also need to be validating that design as you design. So yeah, there you can see the concept that he came up with actually his was, I think, only around 25 megapascals maximum. But this is where we ran through the concept, we ran it through the high fidelity simulation, and it actually came to around 50 MPa, and you can see halved, which is a dramatic difference. So we'll be launching the poll now to get some feedback on the webinar thus far. It should be popping up on your screen now. Please just take a moment to complete that. And this webinar was recorded, so we will be posting it to our YouTube channel afterwards. If you want to just quickly go subscribe to our page, you can scan the QR code. It'll take you right there. So yeah, please subscribe if you want to stay up to date with all of our latest videos. Okay, and then this was our last webinar for the year. So thank you for attending all the webinars we've had this year so far. And looking forward to next year, we've got a few webinar ideas lined up. We've got enhancing and automating your designs with relations, stop doing manual iterations with behavioral modeling, so another way to actually automate part of your design process, and then using the power of ANSYS inside Creo. And then please, if you have any ideas, we'd love to hear from you for what you would like us to cover for next year. Of course, if you want any detailed solution advice or licensing advice, please drop us an email at info@prod1.com or give us a call and visit our website if you're looking for something. I hope you found the webinar interesting, and yeah, I look forward to seeing you next year. Thank you.